So yeah, so the project is about measuring some of the active femoral vents. Those are active since the eruption in December 2019, and the temperature has been enormously high, and which is beyond the threshold of thermal infrared. And it was good to actually do this experiment to identify how we can actually read the temperatures using the shortwave infrared, because the shortwave infrared can detect some of the heat. So I'll just go to the next slide. So the research problem, before going into the research problem, let me tell you how what the problem is, how the data is captured. So we know that Whakaari, or the White Island, is a strato volcano. It's a composite cone, and is a submerged. What it leaves is a surface leaving radiance, which is a reflective as well as emitted, depending on in which spectral band we are looking at it, passes through the atmospheric transmittance, and then it reaches to the satellite. The at-sensor radiance is recorded in the digital numbers, but when we have to convert that back into surface temperatures, what we need to do is to take those digital numbers, take some of those already inbuilt calibration processes applied by the satellite providers, Landsat and Sentinel, and there is a very little input from our end of how we can further calibrate it. But take those results as is, then convert those satellite received spectral radiances, apply the inverse of the Planck function, convert it into brightness temperature, or what we call it top of the atmosphere temperatures. But the bottom of the atmosphere temperature, or the surface temperatures, we need to apply the atmospheric correction as well as assumptions related to the emissivity. So these are certain processes involved to convert it. What we have to do, as I said, the calibration and atmospheric correction issues. Landsat has been available for decades. They have their own processes improved a lot over the period of time. This collection 2 data has been recently available since the start of Landsat 9. And there has been a significant improvement in the data as well as the surface temperatures they are providing as part of the level 2 of the collection 2 products. So the problem is that we have the thermally mixed pixels due to the limited spatial resolution. We know that in a anomalous heat detection, if there is a high temperature present within that pixel, the pixel value would actually show that in a spike in the radiance, and it depends on how it is looked at. For example, in the case of lava lake or in a flowing lava situation, we have the surrounding cold pixels, we have the hot pixels, and in between we have the mix of cold and hot pixels. But in case of White Islands scenario, we have hot vents. Those are generating fumaroles, and that has to be detected in the pixel size of those two sensors operating in the shortwave infrared and in the thermal infrared range. So here is just to show you an idea about how complex the situation is, because the data, Landsat data is captured at 30-meter resolution. The TIRS data, it's TIRS sensor, captures it at 100 meters, but then it is resampled back to 30 meter, and then that information has been provided as a digital number, which has to be converted back into surface temperatures. Sentinel shortwave infrared is a 20 meter spatial resolution. And when we look at over the White Island, their pixels are always on a fixed geometry position, and we know that they are always present there. And these numbers are representing something to us, and we can convert back those into temperatures. The location of some of the active vents have been mentioned here. These positions are not accurate at the moment because the number of different sources which have actually helped in generating these active vent sources are also having their positional alignment issues. As a result of that, we just not have the exact position. And if we know that exact position, we don't know that the vents are heated up or not, because the visual data is not revealing any of the temperature features. So these are pretty much approximation at the moment. So we know that the inverse of the Planck function and how it works, I am not going into that detail. Landsat TIR band saturates when the surface temperature is around 95, 96 degrees Celsius. And if the temperature is beyond that, the pixel saturates and it does not give you the accurate reading. We know that in case of high temperatures, we'll have to rely on shortwave infrared and middle wavelength infrared bands. Pixel detecting anomalous heat appears with a hollow effect in the image. And this is what the case is with TIR, thermal infrared band, when we are dealing with Landsat. Shortwave infrared band can detect fires and anomalous heat in the range of 300 to 500 degrees Celsius if the surface temperature is in this value. Beyond that, the pixel values saturate, and shortwave infrared radiance is not just the emitted radiation, it is also a mix of a reflective and emitted radiation. So we need to minus the emitted radiation by taking the radiance of the cold pixels in the neighborhood and minusing that one. That can minimize it. We'll have to apply the emissivity factor in that calculation. For the sake of simplicity, I just have assumed a constant value because we are just dealing a few pixels and not many around the White Island. So based on that, yeah, there is another point that Landsat and Sentinel have a 80 days tandem revisit possibility, which means they fly on the same date after a difference of 15 minutes. And both data sets can be used if that has been captured without having any issues of cloud or fumarole covering the space. Based on that, we just have looked at some of the initial data, and some of the data is still we have in process. So the 6th of March 2020 image was one such visit when there was both satellites have captured Whakaari Island, and it has been calibrated into surface temperatures and brightness temperatures. The values are much different. What you can see over here is the dots represents Landsat and the diamonds represents the blue represents Sentinel, and the amber color represents Landsat. And brightness temperature is in diamond, and the surface temperatures are in dots. And there is a big variation in the temperature that we have measured. On the ground, we do not have the accurate temperature values for that day, but the nearest one was the 27th of Feb, a few days earlier that visit. And we know that the trend is that there was a very high heat coming out from that system, which slowly cooled down over the period. So we assume that this is the maximum temperature that we were reading at that time. And these are the few boxes. Those are representing how the heat has been, minimum and maximum has been identified over there. The minimum is around 100, but that is around the vicinity of that. So this is also, the minimum is also an anomalous heat, but otherwise the heat surrounding outside the active area is of the temperature range of 25-27 degrees in these times of the year. So using the collection 1 and collection 2 data, and when we have converted back into brightness temperature, we have seen that the TIR image is just giving us the value of around 40-41 degrees Celsius, while the shortwave infrared was reading, minusing the emitted radiance, it was around 250 degrees. So comparing to the actual temperature on the ground, which is, as I said earlier, was around 500 degrees centigrade, but that is covering a much smaller area within the pixel. These pixels have at the range of 40 degrees to 250 degrees in the thermal infrared and shortwave infrared. For the collection 2 level 2 data is more it's more accurate. It's a more what they call it, science product. The temperatures have jumped from 40 degrees to 50 degrees, around 50 degrees over that area. But there has been a significant shift in the pixel high temperatures from south to north. So you can actually see that the anomalous heat pixels in the collection 1 is more southward as comparing to the collection 2 data, which is more sitting as more northward. But the core pixel, which is more anomalous, is still the same pixel. So that has not much changed. In the Sentinel, what we see here, what we see here is around 280 degrees, 270 degrees, and the hot pixel from the thermal, from the Landsat is pretty much in the same area. So based on that, we have to apply a dual band solution, which is when there are two distinct thermal components are available within a mixed pixel. We knowing one of the three properties, the pixel proportion occupied by the hotspot, it is not the aerial percentage of the hotspot, but it has to be the contribution of the heat or the radiance in that pixel. That is the proportion that we need to determine, which is a trickier part. And we need to know the potential hotspot temperature and the background temperature. So in this case, we can assume two of those constants and can run an iterative process. And based on that, we can measure the curves and where they merge together. That is the close proximity of the actual temperature on the ground. And this is what I'm trying to do at the moment. I have not yet completed. The iterative process is still running. We'll have to manually change the process, the values, and then take the values into the graph. So I cannot show you at the moment, but this is what is an interesting problem. If you have any question, please feel free to, excuse me. So please feel free to discuss with me. Thank you.